Hi, I'm Marcel. I'm creating a new programming language and recording myself during the development, like recording the entire thinking process and like designing the language. So this is not a polished video. This series is more like a raw development sessions. Right, so the language we're developing is called Kamin. It's on GitHub, and it's kind of a weird language. It basically combines features from the rock programming language. For example, having type inference everywhere. You can't even specify types, but all of them are inferred by the compiler. And combines that with the compilation time or compile time execution capabilities of Zig. What this allows you to do is to basically inspect the types at compile time. There's a type of function you can use. You can use a function called type info to get information about types. Like, for example, is it what fields are in the type and such things. Right, that's the rough idea. And maybe I'll show a bit how the language kind of looks. Yeah, so these are like types, but you can't write them out specifically. So the idea is that you have a very minimal language where you can just say this is a number, and you define functions like this. So this is a function called not, which takes an a parameter, and then you can switch on that and do different things. And functions are called like this. So just, with space separation. And for each of those calls, the function is compiled with those types. So we have a not function compiled for the type false, which always returns true. And then when we compile not with for, this will result in a compiler error, because you can't switch on a number. You can only switch on these like uppercase identifiers, these uppercase symbols. And the compile time execution will look something like this. So you can ask what's the type of a value and give me information about the type. And this just returns you something very similar to this up here, the true and false, but it returns you, is this an int, is this a struct, and if it is, what fields does it have, and so on. Yeah, that's the basic idea of the language. So what we did so far is implement a few compiler stages. The goal in the end is to generate something, that the CPU can understand, machine code. But we are far from it. So far we have, let me see, we have the source code, which is just a string. We convert that into an indented lines tree, which is a tree where each line of a file is a node. And those nodes are structured based on their indentation, because this is an indentation-based language. Then from that, we pass the content of those lines into I don't remember what the T and O stand for, but basically an abstract syntax tree, a tree that represents the syntax of what you wrote, where the actual nodes of the tree say something like this is a definition, this is a number, this is a call of some name, for example. Then we resolve those names and flatten everything out into an expression guided graph. And yeah, most of the stages have names of breakfast dishes or ingredients. So we have the toast, the egg, and then we type check that and resolve all the types in the yogurt, which is your official graph using resolved types. Right, so we could try and go on from there, basically try to turn this into machine code, probably with some intermediate steps in between. But what we are going to do today, because I don't have a lot of time today, is iterate on this first part of the tree. Because currently you can only basically use ints in the language, which is fine, but the cool thing is that you can have symbols, that you can write false and true, or like anything else that contains an uppercase. You could also just write something in here, and that's valid code. And you know, the actual cool idea of the language is that, hang on, let me add a new slide here. Yeah, it's that when you have a switch, which, you know, kind of branches out the control flow, so you have a control flow, and there are different branches in the if, or different cases, and different things happen in all of them. The only way that types, or new types, are actually created is using, you know, just writing a false somewhere, or writing true somewhere. So here we create a new type, here we create a new type, and here we create another type, for example. Then later, when that switch is complete, all of those branches need to merge. Those control flow branches need to merge into one expression, one value. And here we need to ensure that those types line up. And that will be like the meat of the type system, like the actual interesting part. So this is what we'll probably be working on today. Adding symbols to the language, having an actual like interesting logic in the type system, and maybe working on compile errors and making them like clearer where the error originates from. But we'll see how far we go. Right, so let's switch back to my PC and let's start with some organizational things. So here you see for each compiler stage a file. Kamin is the main file, which imports all those other files and calls those stages. So it reads a file, and then it converts that into this indented lines tree, that into the abstract syntax tree, an expression guided graph, and your official graph using resolved types. Yeah, we also have the here file, which I created before I knew how to call the stage, and that was empty. So yeah, I deleted that. And I also want to rename this indented lines tree because, I mean, look at all the other stages. They're called toast and egg and yogurt. We need something good for this. And I come up with bacon, which is, you know, this is basically a tree of lines, but in programming languages, you often call this, like the line and the column is your cursor position. The line is like the vertical axis, and the column is the horizontal axis. And the nesting of those columns, they determine where a node is placed in the tree. So you could say this is, these are some lines, I don't know, let's call it blocks, arranged by column nesting, or bacon for short. Yeah, I'm not happy with blocks, but nah, it's fine. And also we have the explanation right here. Okay, so let's import bacon instead and make this consistent. And here as well. Right, we need to call this, well, basically everywhere where we say ilt, we want to use bacon instead. So let's replace all of those with bacon and all of those with bacon, and look at that. We have a bacon with a line and children, which is a slice of bacon. Here we have the bacons, and yeah, that looks fine, I think. Also in the next stage, the toast, where we probably have ilts somewhere, right? So those need to also be bacon. Cool. Yeah, turns bacons into toast. This looks fine. Okay. So let's just run this to make sure that things still work. Yeah, this command runs the compiler. So yeah, if you want an explanation of that, just watch the previous video. Line 24 in Kamin. That's true. This needs to be called bacon. Oops. Right. And here we see the stages. So we have a test file with a main function that calls add with 1 and an a. And the compiler is hard-coded to compile the main function for an int argument. So first we pass this into the bacon. Then we have the toast, which represents the structure of the program. Like this is a definition of add, and that's the function that takes a and b and returns a. And having things like calls or definitions or functions or numbers in here. In the expression guided graph, we turn those nested things. For example, if you have a call and one of the arguments is another call, we flatten those out so that we only have a sea of functions, and inside of those functions we have only simple statements or simple expressions, such as this is an int, this is a call. So this determines the order in which operations happen. And lastly, we have this yogurt representation, which contains types for all of those expressions. So because we compile main of int, when we refer to the parameter a, we know that the type of that is an int. And referring to this global add happens at compile time. At runtime, nothing needs to happen here. And the type of that is the function add. The type of this one number is also 1, which is kind of unusual to Martinez. So let's recap the types. There are currently 3 types, three kinds of types maybe. You can have comp time ints, which are ints where the value is known at compile time. You can have ints that are only known at runtime, and you can have functions. Right, so we want to extend that to symbols. Again, symbols are uppercase identifiers like this. And we also want to type check them and so on, but we'll get to that. So first let's just implement symbols. This probably needs to happen in the toast. Actually, let's see what the compiler currently does when it encounters that. Oh, right. It just it passes this like a normal variable reference, and it's like, I don't know the variable named something, and that's true. But all uppercase things shouldn't be variables. So we need to just distinguish between those two. Yeah, here's the parse name function, and I think we want to, I don't know, rename this to parse identifier maybe, and instead have a separate parse name function which just calls parse identifier. But before doing that, it ensures that the first character or the next character is a lowercase character. So just like we did up here, we get the next character, or the current character of where the parser currently is. The parser just walks through the source code. Yeah, if there is none, so we are at the end of the input, then we are like, no, we can't pass a name here. All right, and we need to return that. Nice. Actually, let me hide those files. Yeah, and then we need to ensure that the character is lowercase character, like this. And if it isn't, oops, then we also want to return. Nice. Pass identifier. Why is that? Oh, right, because this returns a string. Okay, and we basically now want the same but for symbols, where we ensure that the symbol starts with an uppercase character. So that down here we can say if we have a symbol, then we want to create a toast.symbol node, which we need to add up here. This is basically like very similar to an integer. You know, if you write a 5 in your code, you just created a new value. And if you write true in your code, you also just created a new value, with the exception that, you know, so I'm going to group that up here instead of those more involved concepts down here. Okay, so int and symbol, that's what we got. Sure, we need to be able to turn that into a string when we print the bacon, oh sorry, the toast. And that's it, I think. That's it for this compiler stage. And in the next stage, when we convert this into an expression guided graph, we need to handle symbols as well. So currently we only have these kinds of expressions. And again, this was, hang on, this was this right here. And now we want something like symbol and a symbol name in here. So let's do that. Symbol with a string. And if we encounter a symbol, we want to create a symbol expression in the egg. Of course, we need to be able to print that. So here we go. Beautiful. Okay, next compiler stage. In the yogurt. Right, here we basically need to extend the type system. So now we don't just have compile time known ints or runtime known ints or functions, but we also have a new type called symbol with a string inside. Yeah, which means we need to be able to write that type very similar to this. Cool. And we need to turn a symbol expression into an expression that needs to do nothing at runtime, but it has the type of that symbol. Let's see what this works. So we have our main function. Hang on, let me open the code in the background. Yeah, the add function down here, it returns something. So, you know, it returns expression number 2 of the type something. So in the main function, when we call the add function with a 1 and an integer, or the other way around. Oh, right, with 1 and an integer, like this, then the result of that is of the type something. Nice. What's the next step? I think the interesting part is actually creating switches. You know, otherwise you can't like branch the control flow. Currently, even though we have functions and so on, the control flow is totally deterministic. The entire program, like, you know which way the program is gonna take. And that's pretty boring. So the first step would be to implement some kind of switch, so you can actually split the control flow and join it later. And then introduce some sort of built-in function so that the value of the switch can be computed at runtime. For example, it would make sense to have a built-in compare function that takes 2 integers. Now let's actually mock that up. It would be nice if we have a compare function that takes an A and a B, and it's like built into the compiler, and it returns less or equal or greater. So one of those 3 symbols. And then, for example, you could use that to define a less than function that takes an A and a B. Okay, I think currently you can't use symbols in names, so it would need to be something like this. And you can switch on, I don't know, compare A and B. And if that's less, well, then we want to return true. If it's equal, we want to return false. If it's greater, we want to return false. And then you can use the isLess function down here and do something based on the result. Yeah, okay. Actually, I don't like that switch as a keyword, because this language is quite minimalistic. You know, you only, like, every name that you write, every identifier means something in the program. You don't have keywords. Currently there are no keywords. You only have the equal sign for declaring variables and functions. So I think it would make sense to have something similar for switch, like perhaps a %, which means that we don't need parentheses around these. And also, like, why a %? I think it looks kind of like, I don't know, like, let me draw stuff. Looks like you have some, you know, if this is the pool of the values that can flow through your program, what a switch does, it basically segments that into like a few independent subsets. And that's basically what the % looks like, kind of, you know, like you have some division between one set of values and another set of values. Yeah, I don't know. But let's try to do it like this. Yeah, I think that's, we can change this later. So I'm not like super committed to the syntax, but it's enough to get us somewhere. Okay, right, where do we do this? Basically in the toast, right? When parsing, we want to check if the current node starts with a %. Yeah. So this would probably be somewhere down here. Yeah, even before we like create a parser and everything. Yeah. If bacon.line starts with a % sign, then this is a switch. Well, yeah, I don't know. So what we want to do is we'll pass the rest of the line as an expression. By the way, up here we will have some return thingy. So yeah, let's maybe just copy this for now and change that later. Right, so we create a parser where the input is the line without the first two characters. Does this work? I think so. Oh. Yeah, I was assuming you would have a percent and an equal sign, but I think we already strip the leading annotation anyway, so yeah, without first. Yeah, I think like this returns the line where at the beginning we cut off the first character. Then we pass an expression, which is like the switch condition, let's call it. And then we have the children, right? And we don't want to just naively convert them or like pass them, but instead we want to make sure that they have an uppercase thing at the beginning, and then colon, and then other stuff. And we don't really need this because you can't yeah, you can't have a percent and then have a definition or something. Okay, so we have the bacon children, and for each child we're gonna do something and then add them to this list of cases, which is currently, I don't know, some type. We're gonna have to figure that out. So for each child of those bacon children, yeah. Oh, right, this can basically happen here. Actually, let's contain it in here. So we create a parser, we pass an expression, we consume white space, we ensure that we are at the end of the line, additional garbage on line, yes. And then this evaluates to the expression, and this is our condition. Nice. And then for the cases, we walk over the basically the indented lines below that. And for each of them, we want to do something very similar. We want to create a parser, but of the entire line. So basically child of line. Oh, wait, no, if they like, let's see, if we have a multi-line call in here, if we have something like this, but it's like this, that should also be fine, I think. Oh, no, this looks weird. I think it should rather be this. Or, you know, this. Yeah. Okay, so for each line, we don't want to pass an expression. No, we want to pass a symbol, which is parser.parse. Parse symbol. Nice. Or panic. Expected symbol of case. Then we want to pass a colon, So parser dot I have this like so often in here. Oh yeah, oh god. Yeah, let's maybe not do that, but instead refactor the parser first to make this a bit more bearable. Have a current function which returns a maybe char. And that's just this. Parser.input.chars get maybe with the parser cursor. Nice. So then each of these just becomes parser.current. Oh, so much cleaner. And actually we can, yeah, let's do it like this. Yeah. Sure. Okay. Do we have this pattern often of like checking a char and then getting the current char, checking it, and then advancing? I don't think so. Nope. Okay. Yeah, I do see this a lot. So let's also refactor that. Advance. We can advance a parser, which returns nothing, and it just says parser cursor plus 1. And then each of these right here they are just parser.advance. Oh, this is cleaner, like definitely cleaner. Okay. Right, so what I wanted to actually do is parser.current, oh look at that. That should be a colon character. This is a character literal in Martinez. And if that's not the case, then expected colon. Yeah, let's see if that, why doesn't that work? Oh, current doesn't need a mutable parser. No. But advanced does need that. Right, this doesn't make any sense. Expect a colon, okay. And then we want to, so there are two ways this can be formatted. Either there should be like a single line expression after that, or that should be the end and the children, or like, okay, either there's a single line expression after that with no children, so like this would be an error, or there's nothing after that, in which case we should have exactly one child, and yeah, then we want to pass that child. Okay, so we do this, and if the parser is done, then we want to do parse single child. Otherwise, parse rest of line into expression, assert that there are no children. Okay, and in the end, we want that to result into in an expression. Yeah. Like this. And then we want to add that to the cases. Like there's cases.push, something that like wraps a symbol and an expression. Okay. Okay, so if the parser is at the end, then we should have a single child, which means that this child, its children should, this child should only have one more child. Oh, this is like messy. Let's call it case, maybe. Oh, right, case underscore. Okay, case.children.len equals 1. Or case with more than one child. Or like with... Okay, can you just write something like this? Is that valid? For now, let's say it's not. Expected one case child. Okay, and then we want to pass that child. So basically do case children get 0.to toast. Like call ourselves recursively. Great. Otherwise, we want to pass the rest of the line into a single expression, similar to what we do up here. We say pass expression, expected case expression, and after that the line should be empty. And we want to return that expression as well. Very similar to what we did above. Right, and we need to assert that there are no children. It's good that I wrote this down first. Right, case.children is empty or panic. Case with that is neither single nor multi-line. Yeah, I don't know. This is a garbage message, but additional garbage on the case line. All of the errors are horrible, like really, really horrible right now. Even that the entire compiler just aborts, as soon as it finds an error, and it's like, well, we just panic. No, in reality, this should return like a result or something, and then display the error in the surrounding source code and stuff like that. Okay, so what we do now, well, we need some way of representing a switch in the toast. Right. We have an int, a symbol, a name, call, a definition, a function. Like these feel very, like top level things. And these feel more like something you do inside of a function. So let's add the switch here, maybe. Or here. Yeah. And we need to have a toast switch. So what's a toast switch? By the way, I'm talking so much, I need to drink. Like, after the last coding session, I was basically unable to talk for 2 days or something. Because, talking for 6 hours that's actually work. Yeah, this session will be shorter, but still. Okay, a switch has a condition, which is a toast, which needs to be a reference because we can't have circular structures that are infinitely big. And it has cases, which is a slice of something. I think it's a new type, toast case, where toast case has a symbol, which is a string, and it has a body, which is a toast. Beautiful, really beautiful. Oh, hang on. I just realized something. What if you want to have like a lot of code in here? You should be able to just do, you know, temporary thing is this, and then I do this, and then I return that. So this shouldn't just be one child, it should actually be... Oh. But how do we deal with that? We have this slice of toast. Yeah, not this, but instead just compile all the children. Yeah, case.children dot to toast, toasts, sorry. Yeah, and wrap that in a toast body. Oh, and these are actually toast cases. And here we create a new toast case with a symbol, which we passed up there, perfect. And a, what's it called? Body. Yeah, body. Yeah, makes sense. Which is the expression. Try to assign toast to field body. Oh, right, because this needs to be on the heap, needs to be a pointer, a reference. Right, and then we have the cases. So the next thing would be to return a toast switch. Oh, sorry, toast dot switch of a toast switch with a condition, which we have here, that needs to be put on the heap, and the cases. Yeah. Oh, that's a vec, but it needs a slice. Right. Yeah, let's maybe break this up into multiple lines. This cases dot to slice. Beautiful. So what's up here? Right, we don't handle that yet. So int symbol name and switch. And symbol name, and if it's a switch, well, what do we want to do? We want to print a percent and the space. And then we want to write the expressions. First the condition. Actually, let's, like, just in here write the condition on a new line. That makes things simpler. So we write the condition, which is the switch dot condition with indentation +1. And then for each case in switch.cases, we basically write the symbol of the case. So yeah, colon and then the body of the case, which will probably be on a new line again. So case dot body with annotation +2 actually. This call doesn't work. Okay, why doesn't it? Oh, it's an end toast. Why that? Doesn't need to be. The case, no. The case can just be body. Because this is already wrapped in a slice, so this is not like it's recursive thing. Okay, try to assign end toast to the body of type toast. Right, here we can just say this body is the expression. And actually let's just name this body to simplify things even further. Cool. Oh, what? Interesting. There were shortcuts for OBS. Okay, nice. This is the next compiler stage. We're done with the parsing of a switch. Yeah. Actually, let's just ensure that the parsing works correctly. So, line 1, 3 in here, let's just be like, hey, switch, I know we need to do stuff here. And compile that. Alright, yeah, for the compile thing we have a weird thing in our test file. Oh, and compare doesn't exist. Like, yeah, there are a lot of things that don't work yet, but look at the switch. We have a switch. Oh no, this is the bacon, sorry. Oh, expected case expression. Is that like, oh wait, for the colon. Wait, what? Oh, right. Yeah, this exactly. Yeah, we expect a colon, but then we also want to consume it. So parser.advance. Mutable parser.advance. Okay, yeah, we reached a to-do. Oh, look at that. Well, this looks horrible. Yeah, let's add a new line here. What? Okay, okay. So we switch on call of compare A and B, and if it's equal, we return false. If it's greater, we return false. Amazing. And actually, let's add the other case as well. Oh, nice. For less, we have this. Okay, so the switch gets passed correctly. Next step would be to, handle the to-do when converting the toast to an egg. Okay, in here we have a switch. Actually, let's first design the switch up here. Ooh. Currently, the egg is completely flat. Is there an egg? Example egg? Yeah, here. It's just a series of expressions. That doesn't work if we have a switch. If we have a switch, then what? Yeah, if we have a switch, we need to add back some hierarchy in here. That's actually sad. But it's the right thing to do. Yeah. So currently the egg fun has a body. And an egg body contains some egg IDs and expressions. And we basically need a new kind of expression for switch, which is like an, you know, an egg switch, which has condition, oops, which will just be an egg ID. And it has cases, which can actually be unordered, so it can be a map from string to a body, an egg body. Does that make sense? I think so. But it makes the egg representation a lot more difficult to work with, because now egg IDs are not as simple as you don't have this basically a function. Before, an egg ID was local to a function, so this 0 is something different than this 0, and an egg ID was just an index into that list inside the function. But as soon as we have like hierarchical bodies and so on, the IDs are not just indices into the, like, there are multiple lists now. That makes things so much more complicated. Okay, or do I like that? Yes, I like that. Let's instead, let's move those expressions up here to the function, like this. Yeah. Which means egg IDs are unique within a function. And, you know, the whole expression ID thing is up here. Yeah. But then a body contains basically just a list of IDs. Which means we have this global list of expressions, but this is not like the actual body. The body contains a list of IDs, which of the expressions that should actually be executed. And then we can have hierarchical structures inside here. And at any point, if we reference an ID, even from like an outer scope, basically, an outer body, we can still look up those expressions really easily in here. Yeah, okay. Ooh, okay. So we have a switch with a condition, which is an egg ID, and the cases are a map from string to egg body. Okay. And then down here, yeah, we need to finish things. And actually we need to probably refactor a lot of this stuff. So currently we have an egg body builder, which just, you know, has a vector of expressions. And now this should actually I think it needs to be split into two components. An egg fun builder containing the actual expressions, and an egg body builder containing the egg IDs, and the parent fun builder. So a reference to that. And actually let's maybe not call them builder but compiler instead. So we have a fun compiler which aggregates the expressions. We have a body compiler which has a reference to the fun compiler, so it can add expressions there, and it has a list of basically the active expressions of this body. Oops. And you can create an egg body compiler like this. Nice. Expression of egg. Oops. Can't type today. Egg IDs. And an egg fun compiler just returns a fun compiler for these actual expressions. Okay, and these, oh right, this needs a parent. So parent being an egg fun compiler. This returns an egg body compiler with that parent. Right, and finishing an egg body compiler means that it returns an egg body. Yeah. While you can push things on there. Yeah, that makes sense. Okay, so you can call toEgg. Beautiful. What's going on here? All right, this needs an egg fun compiler. So compiler is an egg fun compiler, and then we have the egg body compiler based on the fun compiler. We add those parameters and stuff. Actually, let's wrap all of this into something like this. Yeah. Okay, egg body compiler where we add the parameters and then finish that, returning a body which we then use down here. Cool. Yeah, up here we also converted toast to an egg, but we don't need to change anything there. Okay, egg body compiler. What's going on here? Right, we can't push that to the expressions. We need to compiler parent.expressions.len. True. And also the compiler is called like body everywhere else, so I'm just gonna do that. Body.parent.express.len, body.parent.express.push, and body.express.push the newly created ID. Nice. And then in here we have the egg fun with a missing expos field. Wait, we didn't change the egg fun definition, did we? Oh, we did. Okay. Right. So express compiler.express.toSlice probably. Cool. Cool, cool. Okay. And then in here, what's the problem here? If we don't have a function but a value, then right. An egg has definitions which are either a function with a function or a value. But this doesn't make any sense because this only contains egg IDs and it also needs to contain egg expressions somewhere. So I think we need to turn this into an egg fun actually, or even better. I don't know if it's better, but yeah, let's just say this is an egg fun with 0 parameters. Like this is guaranteed to have 0 parameters. Yeah, it's kind of weird, I think, but it's okay. Egg fun compiler. Yeah, and then we create an egg body compiler. Yes, that's exactly what we do. Although we need to do that on the compiler. Yeah, we don't have parameters, and then we finish the body and do something very similar to this down here. Yeah, params are like an empty slice or whatever it is. Empty slice of stores. Beautiful, beautiful. Actually, I think it's kind of weird that the value case is inlined here. And the function case is not. And I think this is only used up there, so let's inline that as well. Yeah, that's an egg fun. Yeah, that. Wait, what? Alright, calling to egg was that. This entire thing is that, right? Like now we have this parallel structure for the fun and for other values. You know, we first create a compiler, then we create a body compiler. And I'm going like back and forth on how I do this, but yeah, look at how similar those are. I could even like factor out creating a compiler. But maybe I'll change this later on, so. Okay. Yeah, this needs a mutable visible thing. Visible.end.define. Nice. And probably very similar down here. Cool. Yeah. Right, this is just an egg fun, which doesn't have parameters, so we just write down the body. Oh. I see. Yeah, this is fun, and this is fun.body. Although I don't know how the body is going to work. I mean, writing an egg body says, well, it just contains egg IDs, you know. So this won't make any sense. Well, no, it won't. It really won't. An express, and that's an ID. So we're going to print the ID, and that's something. Well, at least. Oh, what's that? To egg on with an egg body compiler. Not this one, this right here. Yeah, there's a to-do for the switch. Well, true. So what a switch does is it first compiles the condition, like this, and then it compiles all of the cases. Yeah. Very similar to what we did down here. So cases, and for each case we compile that, and then finally we push an egg expression switch with an egg switch with a condition and cases. Beautiful. And of course this doesn't work because the cases are a bit more complicated than just being arguments. So the cases need to be, alright, this needs to be a map from string to egg body, I think it was. Right, so this doesn't work, but instead what we need to do in here is something similar to like in the end we need to put in here the case symbol and the case body, convert it to an egg. This doesn't work because yeah, this returns an egg ID, true. But we need something that we need to like create a new compiler and compile the body. So basically do body, or a case body, I don't know. Case body is egg body compiler, or actually body.parent, which is the fun compiler. And there we say egg body compiler again. Then we say basically what we do up here in here. So the case body is case body.finish. Yeah. Beautiful. Okay, and then in here we put down the case body. like this. Cool. Yeah, in the cases, like for maps, there's no immutable version, so we just put the cases in there like that. Beautiful. This will probably not oh, this does compile. How does that compile? That doesn't make any sense. Okay. We have the bytes, the bacon and the toast. And then we say unknown reference name compare. Unknown reference name compare. Well, that's true. So let's maybe define a compare, which always returns greater. And let's also remove this with that. Okay. We have the toast. Which looks fine. Yeah, then we have the egg, which doesn't look fine, but that's mostly because the printing is horrible. So let's fix that. Let's say that, ooh, now we need annotation and so on. Well, we can write IDs, we can write an egg by writing the egg body, true, but instead, let's say we can write a body with an indentation, which is an int. And yeah, this does mean that this doesn't work, but instead we have to say, first write a new line, and then write the fun body with indentation 0. And similarly down here, we have to split that up into 2 calls as well. Also, this should probably pass down, I don't know, the fun that this body is contained in, so we can actually access the expression. So let's also do that. And then in here we can say, well, from the function we get the expression with the ID. Yeah, let's add a helper method for that. So on a function you can get an egg ID resulting in an egg expression, so that we say function.express.get id.int. Yes. And that gets us the corresponding expression. So here we can say get the ID. And yes, we need to handle switch. That is true. So if we have a switch, what we do is we just write down switch. And also the condition, so switch condition, which will just be an ID. Yeah. And then for each case in the switch cases, we want to print that as well with 1 indentation more. Yeah. Oh, so this needs an indentation as well. I see. Oh, and the fun. Basically all of this needs to be passed down here. Which means this doesn't work, but instead we have to split that on multiple things. Oops, write the expression. Just remove that. What was that? Well, fun.get with the ID, I think. Also the fun itself and the indentation. Nice. And then in a switch, we also write, new lines and the body. So k is the body, that's right here, and the font and indentation plus 1. Oh right, also the variant. That's pretty important. Case symbol, colon, new line. Yeah, like that. This is not a variant. Okay, that's alright, because it's called switch underscore. And a symbol is not a field on map entry, right? Because those are map entries. So we have not the symbol and body, but the key and the value. Oh, which means those are unordered. But that makes sense, I think. Okay. Oh, this certainly looks weird. And it looks weird because we can't just hardcode this to 2 spaces of indentation, but instead we need to adjust that based on the indentation that we are being given. So, like this. Yeah. And also for the key. Like that. Yeah, I think this needs to be +2. Yeah, that looks, correct, I think. Except that these should be printed with an indentation of 1. Okay, that looks fine. Is less. Oh, look at this. So compare A and B, and then 7 is we switch on 3, and if it's less, it has its own body. If it's equal, it has its own body, and greater as well. Then segmentation fault, which, like, honestly, I'm surprised this even compiles. How, like in the yogurt for switch, we don't do anything, right? We don't handle that. What? Why doesn't this complain? Doesn't make any sense. I mean, okay, the entire egg gets compiled, and it gets, and it gets printed. And I just realized my camera's off for some reason. Right. Because I'm using my phone as my camera and it ran out of battery. Well. Okay. Segmentation fault. Let's investigate this. So at some point we say to yogurt, which like calls this right here a function with, you know, the types that it is supposed to compile to in this. So this is basically just this down here. That in turn is supposed to compile the function. And turn those into yogurt using the yogurt fun compiler. So we have this to yogurt on an egg ID using the fun compiler. That's exactly this. So it says egg fun body express get ID. Oh, I see, which returns an egg ID, which in turn gets an egg ID, and so on and so on. So really what we want to do is egg fun directly contains expressions, and we want to return, we want to turn that into an ID. And we don't represent that as a body. Let's see, we have the main function, which actually probably looks fine. Oh, right, the switch isn't even used. So let's maybe add that as well. Let's say main just compares A to 1. Yes. Oh, that's interesting. It's not in the map. What? ID 7 is not in the map. Yeah, I don't know. I think how would this affect the yogurt fun? The yogurt fun should probably be structured in a very similar way. That we don't have the expressions in the yogurt body, but that they are instead up here, and the body only contains a slice of yogurt IDs, which reference the expression in this slice. Right, so then we have a yogurt fun compiler with a body that doesn't seem right. This should just be expressions. And those shouldn't just work directly on a yogurt fun compiler, but similarly to like what we did in the egg, we also want to have a yogurt body compiler, which, you know, like contains a parent, which is a yogurt fun compiler, and it contains a vec of yogurt IDs. And then you can't push things to a yogurt fun compiler, only to a yogurt body compiler, which I don't know, which is like, hey, let me check the number of expressions in the yogurt fun compiler, get an ID from that, then push the expression to the parent express, and to this compiler's expressions, let's push the ID. Then using a body compiler, you can also get an ID that just looks up the ID in the parent's expressions. And you can also look up an egg ID, let's say on a body compiler. It doesn't really need the the body. These could just be defined on the yogurt fun compiler, but down here we only work with the body compiler, so it's just convenient to have everything available on the body compiler and have the fun compiler mainly as a in the background implementation. Okay, so yogurt body compiler is here. Yeah, let's just see what happens. Right, this is true. Here the body doesn't exist, but this is a list of explos, while the body is the yogurt body compiler, having the parent, which is the compiler, and having expressions, which is a vec of yogurt IDs. Yeah, and then this calls to yogurt using the body compiler. Cool. In the end, we say we have a function with a body. That actually makes sense, but the function also needs the expressions, which are the compiler expressions to slice. And the body compilers expressions aren't set. Okay, we need to create those. Let's maybe add a constructor for the body compiler. We would just body maybe on yogurt compiler. Yeah, returns a yogurt body compiler. By creating a yogurt body compiler where the parent is the parent and expressions is a vec of an empty vector of expressions. Okay, so then in here we could just say compiler dot body. Boom. That's really elegant. And down here in the in the switch and so on, we will also use that. Nice. Then we can push things. We can get things, look things up, and we also want to be able to finish into a yogurt body. Finish with an ID. Probably an egg ID. Yeah, an egg ID. And this will just basically do this. It will create a yogurt body using the existing compiler. Body compiler is gonna be named body throughout this. What is it? We'll just name it compiler, that's fine. Yeah, okay. So the body compiler has the expressions and it returns compiler.parent .egg to yogurt .get whatever the function returns, and that's also compiler.parent .egg fun, I think. .body .returns. That's the ID. That's that we are given. Okay, nice. So in here we can get the expression Oh, by the way, we can also do just this, because on an egg fun you can say get with an egg ID. Turn that into yogurt. Then we put the mapping in here. Sure. Yeah, the parent, true. Sure. Okay. Oh, this is what's going on here. Like that seems bad. Okay, so this is, wait, the fun body expression get type. Yogurt ID. Just that. Okay. Yeah, I know how to refactor that to make it a bit more bearable. Boom! Body is not a field. No, this is called extras. But even better, we can just do body dot finish with fun dot body dot returns. Boom. That's nice. That is really nice. Okay, then up here we have the body expressions. Yeah, this is a yogurt body. Oh, that's basically the same thing as we did in the egg. We need to pass in a fun, which is a yogurt fun, and an indentation, which is an int, so that we can then just go over the body, getting IDs, and then print those IDs with the corresponding expression that we can get from the function. So on the function we can say get the ID, that returns an expression, and we can then get the type and value from that. Of course that get doesn't exist yet. So we need to add that. On a yogurt fun we can get an ID returning an expression, and that's just fun.express.get id.int. Okay. Okay, so down here with the parameters we try to write body, right, and instead of that we need to call write explicitly with that body and the surrounding function and indentation 1, which we also need to use here. So for every indentation level we write 2 spaces instead of just having 2 spaces hard-coded. Okay, and then we print the value, which can be a switch, right? We need to add that as well. Of course we do. Why doesn't this work? Writing a yogurt body. Why is fun? the only thing I want is no segfault. Okay, this is not a segfault, so I guess, yay. Okay, let's see. We have this thing right here. This calls that. I'm wondering, why does it even get so far? Why doesn't it crash down here? That doesn't make any sense to me. Okay, let's see, we convert the egg to yogurt, which means we convert an egg fun to yogurt, sure, the main function, where we convert an egg ID to yogurt and the corresponding egg expression, which at some point is a call to that isLess function. So we convert that. And that compiles everything, including the switch, and then calls finish. What? I mean, okay, if I comment this out, this should, yeah, I don't handle switch. But then this doesn't crash. Like, what? Why doesn't it? Why doesn't this crash? I don't get it. Maybe let's print something. Okay, I don't trust my language enough. Okay, but this. This seems fine on first glance. Why doesn't? Hey. Hey. Let's just, I don't know, yogurting expression. Okay, so we call compare. Like, this is obviously a switch. What we do, let's maybe simplify this. Let's say we have compare that just accepts an A, and this only has two cases, less and greater. Yeah, and let's also say, I think main doesn't call this less, but main just calls that with two things. Well, I think I just closed. That's fine. Okay. This, oh, another error. So yogurting parameter A. Okay, yeah, that's what I expected. Yogurting global compare. Nice. Yogurting 1, 2. Oh, yeah, call to, you know, calling egg ID 1 with egg ID 2 with egg ID 3, I guess, sure. And then we have switch. Wait, no, then we lower that. Okay, you know what, let's simplify this even further. Let's just say we switch on greater. Okay. It's getting like more and more minimal. Yogurting symbol greater. Sure. That's what I expect. But then it says yogurting symbol true. Oh no, oh no, no, I think I know what's going on. In the okay, I expected that when turning a function into yogurt, we would just go over, you know, all the function expressions and turn them into yogurt, instead of going over the body and turning only those expressions to yogurt, but that's not what's happening here. Oh, it is kind of what's happening actually. We are just going over the why do we do it like this? Let's do it like this, and this is already an ID, and then we turn that ID into yogurt. That seems cleaner and correcter. Oh yes, yes, yes. Oh, and I see why. Because, you know, before we just were like, oh, there are, what, 3 expressions in here. So let's lower those 3 expressions. Let's lower the expression with ID 0, ID 1, and ID 2. Because, you know, that code implicitly assumed that the IDs of those expressions were like consecutive. But here the top level expressions are 0, 1, and 4. So, you know, try to compile this, and it kind of worked in this case, or in some cases, and in others it didn't, and stuff got weird. But now it's compiling, like correctly compiling this 4, which is the switch with things inside, and we need to handle that. Nice. Very, very nice. Okay, handle switch. Where do we do that? We do that right here. And the way we do this is similar to a call, I suppose. So getting the switch condition. That's not much different. And then we actually need to have a switch value we can use, because this is not a comp time value. It's also not a parameter, it's not a call. This is a new kind of thing that can happen at runtime. It's a yogurt switch, where we have condition, which is a yogurt ID, and we have cases, which is a map from string to yogurt body. Yes. Written correctly, of course. Nice. And yeah, I think that's more like it. Yeah, of course we need to be able to print that. So for switch we print switch and the condition, and then for each case in switch.cases we write down the case, and here it shows again that we need to pass these down in here, and that we can't just do this naively, but that instead we need to split this into multiple expressions and call write expression value with a function and an indentation. Okay. 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 Right, here we have argument, and of course we don't print it like this, because this is not an argument, this is a case, and in general the case doesn't get printed like this. You just say write the case, which is a body, so it needs to, oh yeah, basically we want to call this up here with fun and indentation +2, because we also write, you know, with indentation the symbol case symbol colon and a new line, and then we write the body for that with more indentation. Okay. Yes, we still need to handle the switch, of course, and that happened down here, where we look up the condition. In the end, we want to create a yogurt value switch of a yogurt switch with the condition and cases. So what do we do about those cases? Those need to be, yeah, that needs to be a map from string to a yogurt body, and for each case in the switch cases we need to compile that, similarly to how we compile functions. So, you know, create a new compiler and so on. Yeah, basically this. Yeah, some parts of this. Right, we create a new body, which is a yogurt body compiler with the same parent as a current compiler. Let's say, let's call it compiler, case compiler. And then for each ID in the case value expressions, we turn that into yogurt. Case underscore. Yes, using the case compiler. So that then in the end we can say case compiler dot finish using the case dot value, which is an egg body dot returns, and this returns a yogurt body which we add to the cases. So cases dot put case key that. Right, and this needs to be associated with a type, which, well, we need to figure that out. We need to extend the type system. For now, let's just say this evaluates to an int, but like that's definitely not correct. Right, and we need to push that. So compiler dot push this huge thing. Whoa. Crazy. So we have a parameter a. We have a greater symbol, which is known at compile time. Then we switch on that symbol. If it's less, then we evaluate to this, the type true. If it's greater, then we evaluate to the type false. What? And yeah, the type of that entire switch is int, which is wrong. Okay, but we are making progress. We are making good progress. Yeah, let's add a new kind of type. So let's maybe add an enum type. Yeah, an enum. which is just a set of symbols. What? Yeah. Actually, we could merge those two types and say that the symbol is also, the type of that is also an enum with just one variant. That's actually similar to what rock does, I think, because in here, if you, if you have a symbol called foo, the type of that is an enum that contains the foo symbol. But you can also like call those. Yeah, actually, I think that makes sense. Only have enums. Yep. Yeah, only have enums. Cool. Right. So yeah, there is no symbol, there's only enum with, oh yeah, how do we call those? I think variance is the usual name for that. So yeah, I think we print those using like, pipe separated things, like, you know, less or greater or other stuff like this. So I'm gonna do the usual thing of saying we have a first thing. If we are the first, then just set first to false, else write a pipe. And then we write down the variance. Okay. And then down here, when we have a symbol, the type of that is not actually a symbol, but it's an enum with a set of the symbol. Oh, right, set doesn't actually exist, I think. Yeah, the general sets in the standard lib are not well supported. And in the future, we also want those, you know, like in rock, we want to be able to associate those symbols with something else. So I think I'm just gonna change it to map. There's currently just maps strings to like nothing, so it's basically a set. But in the future, we'll change this to accept payloads for the symbols. Okay, so this will just be a map from nothing to, from string to nothing. A map with only one map entry. Okay, let's just check if this works. Oh, it does work. Yeah, the type of this is greater maps to nothing. I don't like that. Let's just write down the key. Yeah, writing the type means we write down the variant key. Yeah, the type of that is greater. Cool. Now, the interesting part. Let's join types. The way we do that is in here we have this, you know, this compiler. And when you call it finish, it returns a yogurt body. Actually, let's factor that out. Body is this. And sure, we put that into the cases. But also we want to aggregate the types. And this will just be, you know, a vec of yogurt types. So for each case that we compile, we then need to figure out what's the type of those of that case. So let's just check the body has a returns, right? And that's an ID. And then we can say we want to get the type of that thing by getting that ID, getting the expression, and getting the type of that. So compiler dot get, this gives us a yogurt expression, and this is a type. And we add that to the case types, just like this. And then in here, to do join types, case types. Does this work? Perhaps it does. Yes. Oh, so we need to join the types true and false to figure out the type of the switch. That is super cool. So let's maybe do that. Let's you know what? Let's take a short break. Let me just write down break. And after the break, we're going to think more about the type system and how types can be joined and so on. All right, so let's continue. We were trying to join types. So we wanted to join the types true and false. And before we do that, let's maybe think about how types may flow through the program. So the only way that new types are created is either by literals, such as just writing true or false, or 2 or 5 or whatever. So having these constants in your code. And the other way is by combining types from multiple branches, like combining true and false. But you can't combine everything. So you can't, for example, combine true and an integer. Because the idea is that later on, these types are used to basically, first of all, catch errors. And like, it's not common that you want one branch to return true and the other to return a number. And the other is to ensure that each value can have an efficient memory layout. And if you have an int, for example, the memory layout will just be 8 bytes. So something like this. When the type you have is a compile time known int, such as 5, it actually doesn't need any memory because, well, you know that you don't, like, if the type of something is 5, then you don't need any more additional information at runtime to tell you like what kind of 5 it is or something like that. That doesn't make any sense. Which means if a function, for example, accepts a 5 and an int, then it's actually just given an int. And not actually, like, the 5 doesn't even need to exist somewhere in memory. Only when it tries to call built-in functions which accept only 2 integers, like for example the compare function, then we may need to actually create the 5 in memory or in like some register somewhere to be able to compare the other integer to that. Right, so by default comp time ints, they don't have any size in memory. And something like symbols also don't need to save anything. Only when symbols are combined, like foo or bar. This may actually like we have to store something in memory that tells us whether this is foo or bar, or true or false or something like that. So here this would probably just be 1 byte, and we could even limit this to, like you can only or 256 enum variants, and then we are guaranteed to only use one byte. So basically, if you have a symbol in your code, then this is an opt-in into enum types. This, by the way, for comments, I'll probably use something like this. So, this pipe, this can only be used with types that have a symbol. You can never have something like this stored somewhere. You can, of course, have something like this. So, associate additional data with a symbol. That works, or something like this even. Then you need some memory to store whether this is a foo or bar, and then you need some more memory to store the payload. So you have, I think, 9 bytes in total. That's the idea, at least. Yeah, which means that when joining types, we have to think about all possible combinations, which means we'll probably not do that right here, but instead put this into a separate function. And I think over time it may also make sense to create a separate module for that. For now, I'll just call it join. Join function, which takes 2 types. It takes these yogurt types. So yeah, there is A, which is a yogurt type, and there is B, which is a yogurt type. And it returns a maybe of a yogurt type, because either those types could be joined, and then it's this type right here, but that also may not work. And in that case, we should display a compiler error and be like, hey, this is not working. Yeah, and because we have to take care of all possible combinations of types, this will probably be a pretty long function. Yeah, where we are actually switching over all of these. And currently we only have 4, so this will be fine. But over time, I think this can get pretty complicated. So if we have comp time int, let's call it a int. Then what's the type of joining that with a b? And here's the thing, it depends. If we have a switch and one branch returns 2, and the other branch also, then the result of that is also of the type compile time 2. But if one is 2 and one is 3, well, remember those pipe types, they can't be used for ints or anything. They can only be used if you use symbols, which means instead this will just evaluate to int. So basically we look at what b is, we switch over b. And if that's a comp time int, b int, this definitely works. So this function needs to return a sum. And if they are the same value, so if a int equals b int, then it's actually just yogurt type dot comp time int a. Otherwise, it's yogurt type dot int, so it's a runtime int. Next, what if b is an int? Like a runtime known int. Then the resulting type is also an int. And for all other cases, it doesn't work. Nice. For ints, it's pretty similar. So we just look at b. And in both of those cases, comp time int or runtime known int, it's just going to be a yogurt type int. Nice. Next, enums. So we have the a enum with variance inside, and then we switch over b. Actually, this has to be an enum. If this is an enum with b variance, we do some stuff. Otherwise, this doesn't work. Because you can't join an enum and an integer, or an enum and a comp time int, or an enum and a fun. Enums can only be joined with other enums. And what we do in that case is we want to create a joined enum. So basically we want to build up the result variance, which again, variance for now are just a map from string to nothing, because we don't support enum payloads yet. Yeah. So basically for each variant, an a variance, we add it to the variance. So here we put that variant. And the same goes for the b variance. For now, there can't be, like any mismatch, but later on we would also have to check that if, for example, this returns foo with a 2, and this returns foo with 3, those would need to get joined to foo of int. Yeah. But for now, it's just like this. And yeah, then it returns the yogurt type, the enum, with the variance. Finally, if it's a function, well, b basically also has to be that exact function. So later on, it probably makes sense to have, if you have an add function and a subtract function, we would probably allow something like this. So here you have a compile time known add function, and here a subtract function. We should be able to say, hey, this function, never mind. For each place where you use the function, like where you actually call it, only then the function gets compiled for the correct types. But I could imagine like having something built in, I don't know, standard compile function, where you can basically say compile the add function for some ints. I don't know how lists are gonna look like, or compile the add function for 2 ints and compile the subtraction function for 2 ints, and then we have some functions like for both of those the type is just function that goes from int to int and produces an int. But for now we don't have functions pointers, we don't have anything, like basically this doesn't work yet by design, and we may fix that later. Right, so yeah, we look at b. If it's a function, well, they have to be the exact same function. So if a fun equals b fun, and then this is just this works. Otherwise, it doesn't. And for all other cases, it also doesn't work. Nice. That's basically it, I think. We can join types. Of course, up here, we don't just have 2 types we need to join, but however many cases the switch has. But I think it makes sense to implement the logic for 2 types and then support joining an arbitrary amount of types by like having one common type and joining every type into that. So basically join some types, which is a slice of yogurt type, and yeah, it either works or it doesn't. And so this is a maybe, and yeah, we basically have a common type, which is just the first type. Yeah. And we have all other types just get joined into that. So for each type in types without the first, we say common is, and then we call the function below joining common and that type. Or if that didn't work, we just immediately return yogurt type. We return none. And if that worked, we just return the common type. So we start with the first type, and all other types, they get joined into this type. Cool. So somewhere I think there was a to-do. Yes. We can replace this with join the case types, please. Yeah. Huh. Oh, true. I mean, we could also just say this is A, because A is the same as, yeah, and I think the same applies here. Could just do it like that. This call doesn't work. Oh, because this is a maybe. Right. Yeah, if that doesn't work, no, what we can even, like, I think later on we will have better error handling and so on, so it makes sense to just do that up here. Couldn't join types, and then the case types. Yeah. Oh, look at this. The type of switch is true or false. That's amazing. That is so cool. Okay, how about, all right, let's call this less with A and 1. We check is A less than 1. I don't like this. Oh yeah, I think built-in functions. Oh, this is, we need to check that the amount of arguments matches. Like, definitely. Okay, so we have a compare function, which always returns greater. Fair enough. We have a switch here with 2 cases, and one evaluates to a 2, the other to a 3. And then the entire thing evaluates to an int. That's actually amazing. Okay. Nice. Cool. I think I'll add explicit casts in the yogurt, because, all of the expressions, they have explicit types, so I think it makes sense to have casts somewhere in here instead of just saying this evaluates to 2 and this to 3, and then the result of that is magically just an int. I think. But then again, we could add casts later on if we like actually need them. We don't need to do that now. Yeah. Okay. Cool. I think. Yeah. What's the next step? Probably. I mean, one thing would be to associate like values with enum with these symbols, with these variants. Being able to write something like this. Oh, we should test that it doesn't work. Oh yes. Oh. Right. Yeah, couldn't join times fluent 3. That's beautiful. Wow. Okay. Yeah. That's so nice. Honestly. I love it. Yeah. What else could we do? Yeah, I think having symbols with, allowing this, essentially. That would be nice. And currently that doesn't work because we call something that's not a function. I think that happens in here. Then just search across the entire project. Oh, called probably this. Yeah, not fun. In the yogurt, actually. Okay, so we basically want to switch over what's being called. If it's a function with a function name, then we can, compile the function and do everything that we did down here, right until emitting a call. If it's a symbol rather than an enum, yeah, with some variants. We do other stuff. And finally, in the default case, called, that. Cool, to a yogurt ID. The previous case to nothing, indeed, because in here we need to basically check that the variant doesn't have a payload and that there is only one variant. Right, you can't do something like, I don't know, true equals, this is true or false. Then you can't just do can you do, hang on, foo for. true for or false for? I don't think so. No, that is weird. No. This only works if it's, you know, a simple single variant, just a symbol basically, like here. So variance len equals 1 for an egg called enum with this many variants. Oh right, this is a map, and I think it's called size, like the amount of entries in the map. Right. And what is the variant called? Well, it's called variance dot iter dot next dot unwrap. So basically create an iterator called the next function, which gives us a maybe, and it also returns the only item because we checked that we thought that the size is 1, and then we unwrap it because we know that this item exists. So this is now a map entry with a key, which is the string of the symbol, and a value which currently is nothing, but come to think of it, we should allow probably a slice of other associated types in here. So for example, you know, this entire thing would have the type sum2 1, but you could just as easily like have multiple payloads in each of those, like this. Right, so hang on, enum of map of string and slice of yogurt type. I guess, yeah. So then in here, yeah, this needs to be a slice. But of course we can just create an empty slice of yogurt values. Okay. Oh, yogurt types, true. Yeah, in here we need to join those, basically make sure that they are the same yogurt type. Yeah, like this, and then yeah, all of the variants in A, they are just added right here, and for the variants in B we need to be a bit more careful. Basically, if the A type also has a variant with the same name, then those slices need to, oh, they don't actually need to exactly match, but they need to be joinable. Right, so if variance.get maybe variant key, if that is some, you know, called payload or args, yeah, the arguments to the variant, I think I like that more. Okay. If that is some of those, then we need to check we need to join them basically, and otherwise we just add the new variant from B. Yeah. So here we need to join those into new arguments, which will be a vec of yogurt types, and then for both in zip of, you know, the A arguments, so A args, and the B arguments, so variant dot value. We basically say args dot push the result of joining both dot A and both dot B. Zip returns an iterator that yields tuples. I'm not sure how it handles, like if both of those have different lengths. I do know that it accepts two iterators, so it has to be like this. This call doesn't work because this should be, you know, if those don't match, then we can just, oh sorry, non-figure type. Or we return directly from this join. Right, and then finally we can overwrite the existing payload, yeah, with the joined ones. So with args to slice. Okay. Right, and in here, this is not complete because this evaluates to a variant. This should add something to like emit some expression. The type of that is the new type of that. Yeah, this is just the map entry. Yeah, we need to make sure that the map entry doesn't have any no arguments and no payload is already attached to that. So variant dot value, which is the slice of yogurt types, that has to be empty. Called enum with that already has values. Yeah, something like that, called symbol. Yeah. And then we have the variant key. That's the actual like unique thing that we get from that. Okay, so the return, no, that's not a return type, but it's just the yogurt type of enum of a map where the variant matches to the argument types. Which means we do need to lower the arguments, just like we do here. Hang on. Is that correct? Okay, actually I think it is. Yeah. Okay, yeah, we need to do this like either way. We have the receiver, we create arguments, which is just, you know, going over the arguments and compiling those, well, looking them up, just looking them up. And then we check what's like actually the type of the compiler, of the receiver. If it's an enum, then the result is an enum. You know, we need to make sure that this is just a single symbol, and the result type is right. Wait, hang on. All right, yeah. With that, and probably not a call, but have some new, I don't know, tag maybe. I like to think of this as a symbol, this as a tag, and this, you know, optional with associated arguments as an enum. Just, you know, to get the terminology straight. So this is a tag, and we'll probably have something very similar. A yogurt tag, yeah, with a symbol, which, by the way, is just this, and the arguments. Nice. Oh, those two slice also comes up a lot down there. So let's actually let's remove them from here, and as a result we can simplify this. It's getting more and more beautiful. Okay, nice. So we need a yogurt tag as a new operation, which is very similar to a call, but it works on symbols instead of, you know, functions. Right, so yogurt tag, it has a symbol, which is a compile time known string, and it has arguments, which is a slice of yogurt IDs. Beautiful, honestly beautiful. The yogurt tag, that's like it is up here, yeah. Okay, okay, what? Whoa, okay. So, wait, what? We try to hash a map entry. That doesn't seem right. Oh, at some point I renamed variant to symbol. Where was that? Where was that? Here. Yeah, this also needs to be a symbol. Okay, called type. Type is not in scope. True. Because we basically want to, yeah, no. Let me print this. Okay, you don't handle yogurt value tag. Oh, true. Let's do that right now. If it's a tag, you know, like a create a tag, we just write tag symbol, and then for each arg in tag args. Right, okay, we could have just copied that from down below there, but anyways. Okay, yeah, I know there's a lot of garbage in this file. A lot of garbage. Okay, not quite correct, I think. Let's see, we have a function called isLess. So in here we have, yeah, we call, or we tag sum. We create a new tag with the symbol sum and the argument 2, and the result of that is sum. That's wrong. The type of that should be sum2. So hang on, the value tag is what we did down here, and this maps to the argument types, which seems correct. Oh, I see. Yeah, when we write the yogurt type for now we just assumed that all enum variants don't have anything associated, so we only wrote the key. But obviously, for each of the values, we also need to print that, like each of the payload arguments. So for each argument in, the actual payload, we need to write that as well. Yeah, can just do it like this. Yeah. Okay, so, well, the type of this is none or sum2. What? That's pretty cool, to be honest. And this also automatically allows us to do something like structs, because we can just say, at least positional structs. We can just say, I want to have a tuple of like 1 and 2 and 3, for example. In fact, we can say I have a tuple of 1 and 2, and I don't know, in here I have a tuple of 1 and 3. And we should see that the result of that, yeah, look at this, tuple of 1 and 2, tuple of 1 and 3, and none, adjoined to none, and tuple of 1 and int. What? That's amazing. That is super cool. I mean, you just have the 1 is common among those, so that's the compile time noon 1, but the other number differences, it differs, so it's an integer. Whoa. I like that. I like that a lot. Oh, nice. Super nice. Okay. Wow. You know what, let's maybe commit these things. Hang on, I do have GitHub somewhere around here. Oh, right, I should probably zoom in for the video. Right, so a lot happened. We renamed the built to bacon. We moved the here. We adjusted the egg to parse switches. We the toast to parse switches right here. Yeah. In the egg, we completely changed how bodies were represented. Instead of functions having a list of expressions in them, we now support hierarchical bodies, so an egg switch contains other bodies and so on. And we did the same in the yogurt, added support for function, like symbols and so on. Right. Yeah, sure. I can remove this file basically. Well, I know I should probably make smaller commits that are more focused, but well, add bacon. Symbols and enums. Seems fine to me. Oh, and switch. Let's add that. Enums and switch. Okay. Cool. Yeah. Very, very cool. What else is there to do? Builtins. Yeah. I think the next step would be to have a few built-in functions, like the compare function. And then we can actually think about, going further in the pipeline. Basically starting to think about how can we convert this to C or something. Yeah. Because we can almost write useful programs in this. Yeah. Okay. So let's maybe start with built-ins, I guess. Right, so what are built-ins? What do I mean by saying built-ins? Well, basically, if you have your programming language, you need to think about, this is the language. What parts of the language need to be built into the compiler for this to work? Like, obviously, you can just create numbers like 2 and 3 and 4, and the compiler needs to understand that. But you also need to have some functions built into the compiler, because you can't just, what are we going to implement? We need to, like, for example, if we want to implement a plus function on an add function for integers, we can't just do that in the language. I mean, we could maybe, if like we represent numbers as this memory inefficient, what's it called? Something with P. Pareto numbers or something like that. Numbers per number. Number of there are some languages that just have, for example, a 0 defined, or you can just, for example, we could define 0 using an uppercase Z, as we use the 0 symbol instead of the 0 number. And then for other numbers, we just say we call a successor symbol with something. So that basically we have, instead of writing 3, we would write successor of successor of successor of 0. We could do that, and we could probably implement a print function for that maybe, but it's just pain. And also printing doesn't work, so at least some of the operations of the programming language, they need to be implemented in the compiler. And the question is, where do we draw that line? And how do we draw that line actually? Like for things such as numbers, which are very unique in how they're represented in the source code, that's obvious. But for example, an add function, we need to write something in the source code, or it just magically appears in scope. That's also possible. I think a clean way would be to, for now, just have them magically appear, to be honest. And we have maybe to make things a bit more clear, maybe have a built-in add function, built-in underscore add, and built-in subtract and multiply and divide and so on. And then we can define useful built in, and then the standard library or something defines the add function as just the built-in add function, for example. Or even better, it defines a plus as the built-in add. something like that. But a good way of doing it this way, like instead of the plus being defined by the compiler, we have this function that makes it very explicit that this is built in. And we could even, change plus to something more general. For example, plus could accept an A and a B, and I don't know, then check what are the types of A and B. If they are both strings, then we call, I don't know, built-in string concatenate. If they are both integers, we call, I don't know what, built-in add. And if they are of different types, we can even produce a useful error message and call built-in type of or something to get the type and then get a textual representation and write a nice error message. If we do all of that in the standard library instead of in the compiler, that means the compiler itself can get smaller, and like the surface area of the language is just much smaller. Right. So let's do that. Let's add built-ins. I think it actually makes sense for a new file, maybe. Yeah, I think so. I think let's add a new built-ins file. Also, my camera is lagging. Let's see why. I don't know. I mean, that's probably what you get by using your phone over Wi-Fi as a camera. Alright, so built-ins. Built-ins.mar. I need to drink something. In fact, I do have iced tea. And the next days I'm not at home. I'm cat sitting for a friend. So perhaps it makes sense to drink that. Okay. I won't program for a long time. We'll do built-ins and we won't lower to C, for example, today. Yeah. Add built-ins, and then I think we'll end the session. Okay, yeah, what kind of built-ins do we want? We want add and subtract, compare. Yeah. Add, subtract, multiply, divide, compare. Int operations. Right. And this depends on the standard lib, which we import in the main commune file. Oh, right. I haven't shared my screen. But I'm getting better at this. I'm looking at the OBS thing more often than in the last video, so it's not like I'm programming for 10 minutes and you don't see anything. Yeah. Right, this is the state. We have an enum of built-ins, add, subtract, multiply, divide, and compare. And we'll probably add some more to that later on, but we can spend a lot of time doing that. And this is there are already a few that we implement, but if we have them, adding more is not that difficult. Right. Come to think of it, how are built-ins represented currently? I knew that we had some weird add thing somewhere. Okay, in the bacon, no built-ins exist. In the toast, no built-ins exist because names are not resolved yet. In the egg, here, look at that. We define a built-in add function. instead of just defining a built-in add function, we basically want to define all built-in functions. So for each built-in in the built-ins, what are built-ins? Built-ins are, oh, is there a, I think currently there is no way to get all the values of an enum. Ooh, that's kind of ugly, but okay. Yeah. Okay, I guess that's what we have to do. So for each built-in, we basically say built-in underscore and then the built-in. At least this works. Built-ins is not in scope. Built-ins. Alright, because Kamin doesn't import built-ins yet. Yeah. Right, for each built-in we what do we want to do? Perhaps this is a new enum variant on the name binding. Where do we switch on that? Yeah, we'll probably have a new egg expression, like egg expression.builtin. Or egg expression.global, and we define those in the egg. Yeah, maybe let's do it like that. We have the definitions, which are up there. And for each built-in, we say, well, we have this, this add thing. And then in the defs, we also add that. So here we have the, oh, by the way, add. Let's maybe factor that out. Yeah, and the add name. Yeah, add name becomes an egg definition. Yeah, but that can be built-in. Containing a built-in. Wow, that makes sense. This call doesn't work. Alright, built-in.debug. Yeah, and in here this is an agdev.builtin with the built-in. Cool. And at some point we switch over those. And yeah, built-ins also need to be able to be printed, so we just write. No, this .debug thing is kind of, well, painful. So let's just add a function that writes the built-in. And it just writes the debug thing, so the name. But then we don't have to use debug all over here. Okay, nice. What else? What else? Did we implement the writing correctly? Yes, I think so. What's going on here? Built-in. String, well, this is not. Oh, can you save this? No, this doesn't work. Oh, because it needs to accept the writing. Now it should work. Oh. Yes, do this. you don't handle built-ins in the yogurt. That's true. So in line 190, when we reference a global, and this is a built-in, it's known at compile time, definitely. Now the question is, what is the type? I think the type is just the built-in name, maybe? But this doesn't even make any sense. Why do we do this here? Referencing a global is not... Like, we don't even need to do that. We can just say we always do this. Yeah. And only when we actually, you know, want to do anything with that. That's when we need to switch on that. Okay, cool. Let's maybe use the built-in and just see where things fall apart. So yeah, compare of A and B is not just always greater, but instead it calls built-in compare with A and B. The built-in compare should automatically exist. You know, just magic called global variable. Interesting. Yeah, let's see. So the toast is unchanged, but in the egg we see that we have these built-in functions at built-in div, at built-in compare, at built-in add, and so on. And this doesn't make any sense. Egg. Where's the writing? Here. Like, no. Just do this, I guess. And also just like this, because we don't have any information to display. Yeah, built-in div, you know, it exists. That's all we know. Built-in compare, sure. So then when you call that, let's see. What happens here? We call the isLess function. The isLess function calls the compare function. Okay, sure. The compare function calls the built-in compare function. True. And this is built-in. So then, yeah, when converting this to a yogurt, of course we don't know how to type check those functions when they're called. Called global variable. Called global variable. Yeah, and this is the part where we actually need to switch on this and do completely different things. Well, not completely different things, but you know. Well, we need to do some stuff. If it's a function, you know, then we do this right here. Yeah, we basically just want the return type. That's the entire thing that we like this. yeah, depending on the receiver, if this is a function, then we check what's the definition of that function. Is it, you know, like a real user written function? If so, then we compile this and we get the type of its last expression to get the return value. If it's a built-in, we need to check that. And if it's a variable, yeah, this is when we print this. It's not a variant, what's it called? Value. Called a global value. Not sure. Okay, so we don't need this, because in either case, whatever the underlying thing is, and whatever happens, whether a function gets compiled or whether a built-in gets type checked, we just called it. That's always the same. Okay. Okay, type check compare. Yeah, that's exactly what we want to do. Yeah, and we see that we have these two yogurt of an egg ID, of an egg expression, of a of the entire egg, of an egg function. I think it makes sense that we have a 2-egg with a built-in. Maybe right here before joining types. So converting a built-in with these argument types to a yogurt fun. Let's do it. Or to a yogurt fun? Yeah, perhaps. Yeah. Basically, the main thing we want to do is switch over the built-in. Or actually, let's see how or what we do in the function department up here. In the function department, we just, well, we do a lot of things. We calculate the signature, and we add parameters to a body and do all of that fun stuff. Actually, it should probably be the same for built-ins. Like, of course, they have a very custom body, but they should just be normal yogurt funs, I think. Because they do have the parameters, possibly expressions, and a body, definitely a return value. Yeah. So, yeah, this will just be very similar to compiling a function. So for all of the arguments, we put them in the body. Oh, in here. Yeah. Yeah, but we don't have a function, of course. And we don't need a map from string to yogurt types. No. Instead, we could just say we have a call this arg types. Yeah. The yogurt fun compiler with a body. Yeah, and instead of doing this, this is basically where we want to, to do custom logic. But we don't need the arguments up here. We can instead, oh, I see, that's That's why. Oh, that's weird. That is so weird. I see that, yeah. Okay, let's maybe do something like this. Yeah. I don't like this, to be honest. Yeah, I guess just call it arg_I. And then we have a fun compiler and a body. And then logic. Does the logic also add... No, it doesn't add the parameters. Wait. Before, when we had a yogurt. Yeah. How do these expressions just appear? I think parent A, parent B. Yogurt value dot parent. Oh, because they exist in the ust and in the egg. I see. Yeah, then we have a body and we do stuff. Okay, that's not really what we want to do here, though. Here we just basically want to iterate over the arguments and just always push, you know, yogurt value to parent of the name arg_I with the type args.get I. Yeah, and also args is not args, but args is archetypes. Yeah, and then in here we can have the logic. Okay. Oh, that's kind of not painful, but you know, kind of weird. There doesn't exist an egg fund for this, for example. Yeah, it's... The abstraction doesn't map well to this, I have to say. Having the yogurt fun compiler kind of... well... to do having this, yeah, feels very awkward. Yeah. Well, let's just write this, and we can always refactor this. So if we call an add function, what do we want to do? We want to basically ensure that both arguments are integers. Yeah, so we basically want to if archetypes.len archetypes.len equals 2, that's the first thing. The second thing is, converting the parameters to ints. True, because they could be comp time ints and they can be normal ints, and we need to handle both of them. Let's say, and then we need to emit something inside the function. So I think, yeah, we need a new type of yogurt value, something like, atomic primitive instructions, maybe. Yogurt instruction. And these are things such as add two numbers. These kind of things. Yeah, because some built-ins, they don't need these. They can be implemented using you could have a built-in return a string representation of what's the type of this expression, and give me a string representation for that. You could implement that in like normal yogurt values. You could just create a tag, for example, rather create a comp time symbol that says, well, this is an int, for example, or this is a struct. You don't need any special things to happen under the hood. So some of the built-ins, they disappear at compile time, others don't. And instructions are basically the subset of the actual core things of the built-ins, which don't disappear at compile time. Right, I'm not sure if it's particular to yogurt, probably not. So I will I think I'll put this as an enum in the built-in file. So for example, there's an add instruction and some, all of those above, they should be here as well. But yeah, if we have something like type name, which accepts any argument, and it just returns you a string of the type name. This doesn't need a new built-in instruction or something. This just disappears at compile time and is just like if you wrote a string literal there. Yeah, we don't have that yet. So currently all built-ins map to instructions. But I think it's nice to already have this distinction. Right, so this will be a yogurt instruction, because how that differs from a normal instruction is that this contains an instruction and arguments. So it basically calls an instruction, something like that. Okay, yeah, we have instructions. They need a special. Oh, by the way, instruction means they have a write method, which is very similar to the built-in write method. And what they do is they just write the instruction. And they write the arguments, just like a tag, just like a call. It's a repeating pattern here. Okay, and then in here for the built-ins, we can just say if, for example, we have an add, what we actually want to do is we want to save, like, you know, emit a built-in, emit an instruction. So compiler.instruction, compiler.push, no, body.push, no, body, like this, .push with yogurt value dot instruction of a yogurt instruction, where the instruction is add. And the arguments are, you know, the args. What are the args? Well, the args are defined here as a vector of yogurt IDs, and they are basically this, and converted to a slice. Okay, yeah, like this. So we can have a built-in add built-in. That's going to add a compare built-in, and then have a default case. Right. Yeah, type check compare. That's what we want to do, and we can do that now because now we have the toYogurt for this, for built-ins, where we can pass in stuff. Let's look down here, where we can pass in this. Where is it? Here. toYogurt with the archetypes. The egg, sorry, compiler.parent.egg and compiler.parent.yogurt. Okay, oh, and we don't need this. Yeah. And then we basically want to get the return type of the last expression, similar to how we do it here. And yes, that should be cleaned up. The code should so be cleaned up. 264. Right, the name of this is built-in. Egg fun's fun, and that's not in scope. That's true. Because the yogurt fun compiler doesn't actually match what we're doing here, you know. Well, it kind of does, but not. We don't have an egg fun. That's the thing. We don't have an egg fun. Nope. And that's really sad. Fun is not in scope. Can I own? What do I want to do? Yogurt fun compiler. Do we need an entire yogurt fun compiler? Maybe we don't. I mean, yeah, in the end we need a yogurt fun, but we can like have expressions, and like this doesn't exist, for example, and doesn't make sense. Yeah, I think let's not compiler. Let's just do all of that manually. Let's say we have expressions. Yeah, we don't need this mapping. We don't have a body. We don't need, well, we need this. Yeah, so we need yogurt IDs. Body should be on the back of yogurt IDs. Yeah, and then in here we have the compiler.push, which we don't have, but instead we basically want to, we could create a new body builder that only contains these two things and then define a push on that. It seems a bit like complicated. I'm not satisfied with this design, to be honest. So we have a yogurt body compiler and a yogurt body builder. Really? That's what we want to do? Oh, I guess. Yeah, body is just a bag of yogurt IDs, and it has a push function. That's all it does. With a body, being a yogurt body builder, and an expression being a yogurt expression, returning a yogurt ID. So we create a yogurt ID with an int, which is the body express len. The ID is returned at the end, and then we say body.body.push expr. Okay, so then in here we can say body is a yogurt body builder containing this, and then in here we say, yeah, body.push that expression. Why doesn't that work? Because it's not a mutable body, of course. But now that works, and now we can, yeah, basically just say this. This still works. Yeah, then the function basically has, you know, the parameters. The expressions and a yogurt body with a returns thing and a body, so express, and that's, let me think, body.body. Oh, that's nasty. I mean, look at this code. Oh shit. Okay. Yeah, we basically want the last expression of the body to implicitly return here. Oh. Not nice. Really not nice. But yeah, we build the correct function and then we do this over here. Well, yeah, push the expression, push the ID to the body. Okay. This call doesn't work. Push a yogurt value, no. This needs to have a type. Yogurt type dot int. And the type of this is actually interesting. Let's give a type dot enum with a map and other. other stuff which we'll get to now. So we have this. Yeah, we basically want a string. It's either less with an empty slice of yogurt types or equal or greater. No, we're not aligned them, right? Okay. Param says the type slice of still. Of course, is params used anywhere, or is that just, I think it just exists for, I don't even know what. Yeah, we don't have that here. Yeah, these are actually more like archetypes. Sorry, param types. And yeah, these are the params. Oh, but yeah, let's leave it at archetypes, I guess. I'm fine with that. Right, so we need to create params. Oh, let's just do that locally down there. Params is creating a back of store, and then we say vec push this. Okay, and then we return the back to slice. Okay, cool. I'm fine with that. Whoa, 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 look at that. Okay, this is actually cool. So in the yogurt, we only have the functions that are called, which means we have the main function. Oh, that's nice. And you can see in here it takes the is-less function, and then it calls the is-less function with, you know, let's actually write code that doesn't neglect the brain that much. Let's make it so that the is-less function returns true if a value is less and false otherwise. That seems reasonable. Okay, so yeah, we call the is-less function, which returns a true or false. You know, let's just do that and then worry about other things later. Okay, here's main. Main just calls is-less with an int and 1. So then let's go to is-less. Oh, that's nice. Is-less of int and 1. It takes those parameters, takes a compare function, and calls the compare function with an int and 1. So what's the compare function? Well, the compare function for int and 1 is defined down here. Takes those, calls, you know, built-in compare. And built-in compare is implemented by the compiler. Built-in compare of int1 has parameters arg0 and arg1, accesses them, and then has an add instruction. Okay, yeah, which returns less or equal or greater, because sure it does. But then it returns that. So we see that, you know, compare also returns less or equal or greater. So this call to the compare function returns it results in less or equal or greater. So we switch on that, and less, equal, and greater. We do different things here. We evaluate to true or to false. So then this entire switch evaluates to true or false. That gets returned. Nice. That's actually nice. Like, that is super nice. Okay, one thing I noticed is that we don't actually ensure that all variants are handled. So I could just do this, for example. That's bad. But we can actually fix that, because we know that the type of this 3 is less or equal or greater, and we only handle less and equal. So when type checking, so when yogurting a switch, we don't just want to go over all the cases, but instead we want to go over cases that over all cases that can possibly occur in the value. For example, if we have if we compare is less with 1 and 2, actually we only want this path to be compiled. And that's not like an optimization or something, that's like actually the language spec, that the language guarantees that. Because if we have a format function and we say type info and value, I'm going to switch on that. And if it's an int, then I call, I don't know, add value 1. If it's a symbol, then I don't know, I just return it if, stuff like this. In this case, if we compile this call for each value, like for example, if we call format with true, we don't even want this call to be compiled, because that will result in a compiler error. Adding true and 1. That's the power of Zig, by the way, that it guarantees to only compile branches where if the type or the value of the condition is known at compile time, then it guarantees to only compile necessary branches. And that's what we want. And that's also a great opportunity to ensure that we handle all the possibilities. So rather than going over all of the switch cases and compiling them, we instead want to go over all of the, we want to look at the condition, basically. Lookup returns what? It returns a yogurt ID. And then we can get that to get a yogurt expression. So condition type is compiler.get condition.type. And that has to be an enum. Otherwise, condition variance. If that's not an enum, that's an error. You can't even switch over ints, for example. Switch is reserved for enums, at least for now. Maybe later we'll have more general pattern matching stuff, or I don't know what. But for now, switching only works on enums. Yeah, and then rather than going over all of the switch cases, we instead go over all of the condition variants. And for each variant, we get the corresponding switch case. So, you know, switch.cases.get the case for that variant, please. If that doesn't work, you know, switching on condition variants but this variant is not handled. Yeah, basically I want to print the type. Yeah, condition type is this. Let's maybe inline that down here. Because why not? Yeah. We get the condition type. And then no, that's also ugly. Okay, like this. Let's leave it like this. Yeah. Switching on condition type, but variant is not handled. Beautiful. Honestly. Get maybe on a map. Oh, the map entry. Oh no. Variant condition. What do they have? They have payloads, right? Alright, we also need to check that the payload lengths they match. And bind things to those payloads. I think that's not supported right now. You can't attach, like, yes, you can attach payloads, but you can't like unwrap them. This doesn't even get passed. So for now we'll just ignore them and deal with that later. Yeah, we just need to check that this works. Okay. And then when we found the case, we compile it. Only then. What? Yeah, put variant key, body, okay, perfect. Right, I don't need this. Okay. So this works, but if this is missing, for example, this doesn't compile. Switching on less or equal or greater. Compare returns less or equal or greater, but greater is not handled. That's pretty cool. That is pretty cool. Okay. Nice. Really nice. Okay, that's one thing. So let's maybe commit that. Yeah, add built-ins and oh, hang on. In the built-ins there was this weird error that we emitted an add instruction for compare. Add built-ins, instructions, and check switch exhaustiveness. Yes. Great. Okay. To be honest, I think that's it for today. Yeah. Cool. So that maybe, I know that this was a shorter coding session than the last one, but yeah, I think we did we really dove into the deep corners of the type checking, like unifying branches of a switch and only compiling branches that are there, catching if a branch is not handled. All of that is super cool. Plus, we started implementing built-ins, and for example, in a later compiler stage, whenever we find, this built-in, whenever we find an instruction that's already quite, it's very low level. What I'm trying to say, this basically compiles to, I don't know, a few CPU instructions in the end, something like that. So there is not much to do before like lowering to C or something. Yeah. Cool. We have more type checking. We have more types. We have symbols. We have enums. We have switch. I think that was okay. An okay coding session. I think not as productive as the last one, but also not as long, and definitely more heavyweight and more unique to this language in what it needed to be done. So I hope that was interesting, and I guess until next time, bye.